Hello everyone. In this video lecture I will be covering your 4th semester laser physics course. This video lecture will contain a brief overview of your laser physics syllabus. For details and for the exam point of view, you will definitely have to look into your textbooks and reference books. This will help you in developing a basic understanding of the subject. So let us begin with the lecture. So first of all, what are lasers? So laser is an acronym for light amplification by stimulated emission of radiation, LASER. So as the name suggests we need to amplify the light by a process which is called stimulated emission of radiation. So how the whole game is how this stimulated emission of radiation is achieved. How do we stimulate a medium, a material in such a manner that it produces laser light? Okay, so what happens is you have a medium, it could be a gas, a solid or a liquid. We excite that the atoms of that medium to higher energy levels, and then the material, it comes down to lower energy levels by emitting energy in the form of light, and that light is somehow converted into laser beam. So these are lasers, right? So now we will discuss in detail how a laser device is made, how the laser action takes place, and how a laser beam is obtained. So first of all, how are lasers special? What makes them special and what makes them different from the ordinary light which we get from light bulbs and tube lights? So how is it different? As we might have seen already laser light somewhere in our lives. The laser light is very sharp in the sense it is very high in intensity. It is highly directional. You can say it is ideally unidirectional. That means it is a strong, intense beam of light which travels along a straight path up to very large distances, right? So what are the basic properties of laser light? First of all, it is a directional beam. As the picture itself, it makes it clear that the light bulb, it emits light in all directions, random directions, but the laser light is unidirectional. It is emitted along a straight path, right? And the second property is it has a narrow spectrum. So what do you mean by narrow spectrum? That the ordinary light which we get from light bulbs and tube lights, it is generally white. White, what do we mean by white? It has all possible colors. The spectrum is large. The various frequencies of lights are present in ordinary light, but in case of lasers we have a sharp bandwidth. Almost monochromatic light is obtained, almost monochromatic. Okay, we try our best that when a laser beam is being produced that it has to be monochromatic, but ideal case is never achieved, right? So next, the third property is that they are coherent. Laser beams are coherent. As you can see, the picture itself illustrates it very nicely that the light from the regular bulb is not coherent. It is not traveling in a uniform manner, but the laser light is very coherent. It is uniform in nature, right? So from the exam point of view, you will have to make a detailed study of the properties of laser light. They are very well described in your textbooks. Okay, now for so long we have been talking about emission of radiation. Okay, some radiation has to be emitted from a medium that will form the laser beam. So how did we come to this conclusion that we need stimulated emission of radiation for a laser? So this concept was first proposed by Einstein. He gave a theory that whenever some kind of radiation interacts with matter, three kinds of processes are possible. So light can or radiation can interact with matter in three ways. Okay, what are those three ways? First one is called absorption, and the second is emission, right? So there can be absorption of radiation and there can be emission of radiation. Now this emission is of two types, further of two types. One is spontaneous emission and another is called stimulated emission. So all in all, we have three kinds of processes which are possible whenever radiation is incident on matter or radiation interacts with matter. So what are those three processes? Absorption, absorption, and two kinds of emission: spontaneous and stimulated emission, right? So he gave a basic theory for this these kinds of interactions. What he said was, he said that okay, three kinds of processes are possible. The first one and the most basic process which happens is whenever radiation is incident on some matter which has a large number of atoms in it in ground state. So those atoms, they absorb the external radiation and jump to higher excited state. So this is the simplest kind of process which can happen whenever radiation falls on matter. So atoms in ground state will absorb energy and jump to higher excited states, right? So these excited states then, when they absorb light, which is a light radiation which is being supplied externally, this process is called stimulated absorption. Why stimulated absorption? So whenever there is some external interference, some external source is required to carry on the process, that process will be termed stimulated. As we'll be seeing later on, all the processes which need external intervention will be called stimulated, and which we don't need any external stimulation and they act on their own, they will be termed as spontaneous, right? So the first and the basic process is stimulated absorption. So what Einstein stated, he said that rate of the stimulated absorption will be proportional to number of atoms. N1 are the number of atoms which are in ground state at that particular point of time. Okay, so obviously the rate, how much radiation is being absorbed will depend on number of atoms which are already in ground state and need that absorption, who can afford that absorption. So the N1 and I, what is I? Intensity of the incident beam. So definitely if the radiation which we are supplying to the matter, intensity of that external radiation will play an important role in rate of absorption. So he said that stimulated absorption is proportional to number of atoms in ground state and the intensity of incident radiation. Now this rate was proportional to N1 and I, intensity of incident radiation. Now he removed this proportionality constant and introduced a coefficient called B, which is known as Einstein's coefficient for stimulated absorption. So this is the rate equation, Einstein's rate equation for stimulated absorption. Clear? Next, the second kind of process which Einstein stated was stimulated emission. Okay, so before we discuss stimulated emission, we need to discuss spontaneous emission. What is happening in spontaneous emission? Now we had seen earlier that whenever the external radiation is provided to the matter, what happens is the atoms in the ground state, they absorb the radiation and jump to higher excited states. Now what will happen? That all the excited states of a material, they have an average lifetime of 10 raised to power minus 8 seconds, right? So any atom will remain in the excited state for 10 raised to power minus 8 seconds. After this time period, the atom will automatically jump back to its ground state and emit energy, right? This is spontaneous. It will happen. Come what may, it will happen. You don't need to interfere or intervene or provide any kind of external stimulus to the atom for that. Atoms in excited states will automatically jump after an average time period of 10 raised to power minus 8 seconds. This process is spontaneous emission of light, right? So this spontaneous emission, he said the rate of spontaneous emission will be proportional to N2. And what are N2? Number of atoms in the excited states. And A is known as the Einstein's coefficient for spontaneous emission. Then the other kind of process which is possible is stimulated emission. Now this was spontaneous emission. Now we are talking about stimulated emission. It means for energy to be emitted, we need external stimulus. What we do is, when the atoms are already lying in the excited states under the time period of this 10 raised to power minus 8 seconds, we provide some external stimulus to these excited states, not to the ground state. I'm talking about the excited state. So when external stimulus is provided to these excited states, what happens is these excited states will either the atoms which are already in the excited state will jump to further excited states and emit energy in the form of photons, or what will happen is meanwhile they are in during the time when they are jumping down to the ground state, they are again re-excited. So the same atom is capable of emitting energy 2 times or multiple times, or whatever it may be, right? So this stimulated emission, whenever it happens, it leads to amplification of light because a larger amount of energy per unit atom is being emitted now, right? So this stimulated emission, that is why our laser is stimulated, is light amplification by stimulated emission of radiation. Okay, stimulated emission is the basic process which is required for laser beam, for constructing a laser beam, right? So this stimulated emission was defined by Einstein as proportional to into number of atoms in the excited state, because we're talking about the excited state, into the intensity of the incident radiation. Now here also the intensity of the incident radiation matters, because this incident radiation only will stimulate the atoms in the excited state, right? So these are the rate equations, Einstein's rate equations for light emission and absorption. Now these rate equations are used to evaluate the Einstein emission and absorption coefficients. A and B coefficients, they are obtained by solving these rate equations, right? So these detailed derivation and derivation of these Einstein's coefficients is very beautifully given in your textbooks. So you are required to study that whole derivation from the exam point of view. It is important. Next, now as I have already stated that the process which contributes to laser beam production is stimulated emission, right? Now what stimulated emission, that means we need a large amount of atoms in the excited state. Only then we will be able to achieve a state where a large amount of photons, energy in the form of photons is emitted outside, when we have large number of atoms in the excited state rather than in the ground state. But what actually happens is, now naturally the number of atoms in the ground state at equilibrium are far more than atoms in the excited state, right? Now if we don't have atoms in the excited state, what happens? No emission of radiation will occur. So whenever we are providing external energy, we are pumping the atoms in ground state too, so that they can turn to higher excited states. So as the picture here it illustrates that we want a lots of this. Lots of this means we want a lots of atoms in the excited state, so that they can jump back to ground states or lower energy states to emit light. And we don't need this. We don't need atoms, a good number of atoms in the ground state or the lower energy states. We don't want absorption. Absorption is not needed for laser beam. What we are interested in is emission of radiation from the higher energy states. Now, since naturally at equilibrium we have more number of atoms in the ground state, this is the natural condition. What we need is the opposite of that. We need larger number of atoms in the excited state. So this condition is known as population inversion. We need an inversion of population of atoms in excited states rather than in the ground state. So this population inversion is the basic condition for achieving laser action. Right? So now what happens is, whenever we have atoms, they need to jump to higher excited states, right? And they will jump back again to ground state to emit energy in the form of light or whatever. Now what happens is that we know that the excited state of atoms has a very short lifespan of 10 raised to power minus 8 seconds. That means for a very short period of time the atoms will be in the excited state. we need to exploit this 10 raised to power minus 8 seconds time period. Now it is very difficult to achieve a laser action in this short period of time. So what we have resolved to achieve population inversion or to achieve the laser action, what we have resolved is that we will introduce a metastable state. Metastable state will be externally induced in the main medium, laser medium. This metastable state, which literally means temporarily stable state, which will have a time period of 10 raised to power minus 3 seconds, which is very great, very large than 10 raised to power minus 8 seconds. Okay, so now this metastable state is comparatively stable than the actual excited state of the atom, which lives only for 10 raised to power minus 8 seconds. Now this metastable state will offer us a longer duration of time, so that we have a large number of atoms accumulated in an excited state for a longer period of time. More the number of atoms in the excited state, longer the period of lifetime period of the excited state, the better laser output we will get. So what we need is a stable, more stable, higher excited energy level other than the actual excited energy level of the matter or the material which we are using for lasing device. Okay, so how are these metastable states created? These metastable states are created by introducing some kind of external impurity in solids, or some external gas mixture is mixture of gases is used, so that because different materials will have different energy levels, so these different energy levels will give a more opportunity to atoms to accommodate in different stages, in different energy levels. So a more number of states are available when there are a mixture of materials. So by adding impurities to solids or creating a mixture of gases, a mixture of liquids in the main lasing medium, we introduce metastable states. So we'll be discussing it a little detail later on, right? So metastable states and population inversion, these are the basic conditions for lasing action. So now we understand that we need population inversion of levels, energy levels, right? And we need a metastable state, a comparatively more stable state than the excited state to achieve the laser action. Now we have a metastable state, and we know that we need population inversion. To achieve population inversion, a process called pumping is done. What is pumping? It is simply excitation of atoms in ground state to higher energy states. Pumping can be done by different methods. Okay, so these are the what different methods? Like there can be optical pumping, there can be electrical discharge method or electrical pumping, and there can be direct conversion of atoms in the ground state to a higher energy state by collision or some other method, right? Then there is elastic atom to atom collisions. This method is generally used in gas lasers. So what happens in optical pumping is like especially in solid state lasers. What are solid state lasers? I'll be discussing it later on in this presentation. Solid state lasers are those lasers which use a solid material, a solid medium for lasing device, right? So in this case, what is done is we have external radiation which excites the atoms in the solid to higher energy states. In electrical discharge method, what happens is that we have a mixture of gases, and this mixture of gases is placed in a discharge tube, and with the help of electric current, a discharge is produced, and the excited electrons which are produced by the discharge, these electrons collide with the atoms of the main medium, the gas medium. These electrons collide with them, and the atoms are excited to higher excited states. Then there is direct conversion, which happens in semiconductor lasers. Semiconductor lasers, we all know that we have semiconductors have a band structure. They have a conduction band, they have a valence band. So what happens in this case is that the atoms of the medium, the semiconductor, they are directly raised to higher energy states. Then we have elastic and atom to atom collisions. What happens is in these gas lasers, external gas, another gas is added to the main gas medium, and these gases are made to collide with each other, and these collisions lead to excited energy states of main medium atom. Okay. Next, Now we have been talking about population inversion, pumping, and metastable states. So based on these metastable states, the lasers can be classified into different kinds of level lasers. Okay, how many levels are there? How many energy levels are present in the main lasing device? So according to that, on the basis of that, the lasers can be classified into 2 level, 3 level, 4 level, and so on. These kinds of lasers are available. Now here we are discussing 3 level laser direct away. We are not talking about 2 level laser. Why? 2 level laser is not possible. Okay, laser action is not possible to, to be achieved in 2 levels. When we have just 2 levels, one ground state and one excited state, laser action cannot be achieved. Let us suppose this is our ground state E1 and this is our upper excited state E2. We have just 2 levels in the lasing medium. What will happen in this? We have a number of atoms in the ground state. We pump it, the material, by the process of pumping, we excite these ground state atoms to higher energy state, and they will spontaneously decay back to original energy state. Now this will happen spontaneously. Okay, either if we provide some external stimulus to these excited states, they have nowhere to go. Okay, they will ultimately jump back to this same ground state. So there is no amplification taking place, right? So 2 level laser is not possible. Its mathematical proof is given in your textbooks and it is important. So you must know how, if a question is asked in your exam, why is 2 level laser not possible, right? So its mathematical proof is also given in your books. You must read that. So if 2 level laser is not possible, definitely we need to introduce a third level, that is known as the metastable state, the third level state. Okay. So when this third level state is introduced, the laser is called a 3 level laser. We have 3 levels: ground state, excited state, and a metastable state. Now what happens in a 3 level state, 3 level laser? Atoms in the ground state are pumped to excited state, right? Now when they return back, okay, now they when after 10 raised to power minus 8 seconds time period, when they try to return back to lower energy states by losing energy, what happens is that they have a possibility, they have this level to jump to, this and this. Some will directly jump back, some will come to this level, right? Now this level, because it is very much closer in energy to this upper level, there will be rapid decay from this level to this level. Now this level, since it has a lower energy, it is comparatively stable. It has lower energy than this upper level, so it is comparatively stable. And atoms, when they decay back, rapidly decay back to this. Now this rapid decay, I would mention here that this rapid decay is non-radiative in nature. Non-radiative. You will read in your textbooks also that the radiation emission is of two kinds: non-radiative and radiative emission of energy. So this rapid decay from E3 to E2, from excited state to metastable state, is a non-radiative transition. In this, what happens is that the energy that is radiated, that is emitted out, is not in the form of radiation, rather it is in the form of phonons, or or we can say in the form of some kind of vibrational energy, not in the form of an electromagnetic or radiation, right? So this is non-radiative decay. It rapidly decays into the metastable state, and we have, as a result, because this is a relatively long-lived state, we have a large number of atoms. Some may have also jumped from the ground state to this metastable state directly. So at any point of time, we have a large number of atoms accumulated in this state. Now whenever these large number of atoms will jump down to ground state, they will emit a lot of energy. So the intensified and amplified radiation is what we will receive. So this will help in getting us a laser beam, right? Then after this 3 level laser, we can also have 4 level laser. As it is our common sense would suggest that obviously the 4 level laser will be more efficient. It will provide a better laser beam than 3 level laser. Why we have that? Because we will have, in a 4 level laser, we will have 2 metastable states, 2 extra states. 2 extra excited states means larger number of atoms in the excited states and a better emission of radiation. right? Now what is happening in a 4-level laser? We have two metastables, E2 and E1. Okay, now whenever atoms jump from ground state to excited state by pumping, they have what will they do? They will undergo non-radiative transition in the form of phonons, and they will jump back to phonons are quanta of sound energy. Uh, you will be studying this in your final year condensed matter physics course. So for time being, they are quanta of sound energy or quanta of vibrational energy. So whenever atoms vibrate, they transmit energy in the form of phonons. So when electromagnetic waves they transmit energy, they transmit it in forms of packets called photons, and the vibrational energy is transmitted in the form of phonons. Okay, this is for your information. Now this non-radiative transition occurs and the atoms jump from higher excited state to metastable state, right? This state. The same procedure which has happened in the 3-level laser occurs here also. We have a lot of atoms accumulated in this metastable state at a point of time. Now what will happen is, now these atoms in this excited state will jump back to this another state which we have introduced later on, E1, and then after jumping back to E1, then again they will undergo non-radiative transition, and they will end up in the ground state. What is happening here is, why is it better from 3-level laser? If in case of 3-level laser we have only 3 levels, right? Now we have 2 levels and the laser is being formed here between E2 and E1. We have reduced this energy gap. Now since this energy gap is reduced, it means the emission of amplified light will be more rapid, so better output can be achieved, right? So these were the types of lasers based upon the number of metastable states. Then now we have discussed how a laser beam is produced, how we amplify the light. So now we will discuss what are the basic components of a laser device. So what instruments or what components are used to make a laser device to generate a laser beam. First of all, we have an active medium. We have been discussing since start of this presentation. We have an active medium which is excited and which is de-excited to emit radiation, right? This active medium can be a solid, can be gases, can be liquids, can be semiconductors or whatever. On the basis of the nature of the active medium, lasers can be classified into different types, which we will be discussing later on in this presentation. Right, now we have active medium first of all. Then we have a pumping source. I have discussed it that pumping can be of different types: optical, electrical, collisional. So all those pumping mechanisms need a source, energy source, external energy source. So we need a pumping source for the purpose of to achieve population inversion. Then we have a resonance cavity. All this pumping source and active medium, they are placed in a resonant cavity which has two mirrors on the sides, mirrors for reflection. One of the mirror is completely polished so that it can give 100% reflection, and one is partially polished so that the emitted light can be transmitted outside, from where it can be collimated into a laser beam, right? So these are the basic 3 components of a laser device. Next, now we are talking about that, okay, we have an active medium, we have excited it using a pumping source, and then we have placed them in a resonant cavity which includes 2 well polished mirrors. Reflections occur in this resonant cavity, and after suffering multiple reflections, light comes out in the form of a laser beam. Now we all know that whenever light travels through a medium, its intensity is naturally expected to reduce whenever it passes through a medium, especially solid medium or any opaque medium or any semi-transparent medium. Whenever light travels through a medium, it is expected to lose its intensity. That means there are losses. Okay, so naturally there must be losses, but what we need is gain. Okay, we need the intensity of the emitted light to be higher than the incident light, so that is again opposite of what naturally occurs. Okay, so that means there should be a threshold condition which defines that at least The in this diagram, as you can see, that this is the incident radiation. It travels through this medium, and it is emitted out from this medium. It is reflected back from this medium, and then a part of it is transmitted out, a part of it is reflected back. It again travels to this medium and is emitted out as I3, and it is again reflected back. Now, to achieve laser action, what we need is that this I3 has to be quite large than I0. Then only laser action can be achieved. So we need to overcome these losses. These losses have to be overcome to produce a beam that has a gain in intensity. Okay, now how is laser gain then defined? What happens? That generally whenever the light will pass through a medium, it will lose its intensity, and the rate of change of intensity with length can be described as the rate of emission minus the rate of absorption, right? Now this threshold condition for laser gain is also very nicely described in your textbooks. I would request you to look into textbooks when seeing this topic, right? So the rate of loss will be proportional to the rate of emission, that is the rate of gain, minus the rate of absorption, rate of loss, right? So this can be further simplified into I0 is the incident radiation, and the decay which happens naturally. The decay of intensity that happens is exponential decay in terms of sigma n2 minus n1 into z. Z is the length of the medium through which the light is traveling. N2 are the number of atoms in excited states. N1 are number of atoms in the ground state. Right? Now what happens is when you have a large number of atoms in the excited state, then N2 will be greater than N1. When N2 is greater than N1, this whole quantity will be a positive quantity. When it is positive, it means the intensity, resultant intensity, is increasing exponentially. When it is increasing exponentially, that means there is a gain. That is what we need. Okay, and if the N2, the number of atoms in the excited states, are less than a number of atoms in the ground state, then what will happen? This quantity N2 minus N2 N1 will be a negative quantity. When it is negative, it means there is an exponential decay. When there is decay, that means losses are more prominent. So that is what we don't need. What we need is gain, which is defined by N2 minus N1 into sigma, where sigma is the absorption coefficient of the medium. It is dependent on the nature of the medium. So this is how the gain of a laser beam is defined. It is exponential. We need exponential gain in the intensity of light, right? So we have been discussing all this, the formation of laser beam and how the intensity of an ordinary light beam is multiplied, is amplified to form a laser beam. Now whenever laser beam is produced, obviously our main concern is that we should get high quality laser, which should give us more output as compared to input, right? So based on that, the nature of output, laser beam output, we can distinguish laser types, right? So there is continuous wave laser, pulsed laser, Q-switched laser, and mode locked laser. What is a continuous wave laser? It is a continuous beam of light as long as the medium is excited. A continuous beam is being emitted from a device, right? Generally what is there is that this continuous wave laser is generally its power is low. Intensity is not that high when we have a continuous beam being emitted from a light generally. Okay, and this pulsed laser is that pulses of lights, small pulses means duration of pulse is quite low. Femtoseconds or to a few seconds pulses are obtained. These pulses are generally, they have intense power. They are comparatively intense in nature than the continuous wave lasers. Then we have Q-switched lasers. Q stands for quality factor of laser. Now this quality factor, what is the expression for this quality factor, and on what factors this quality factor of a laser beam depends? You need to see your textbook. I would recommend you to see your textbooks for quality factor derivation. So based on the quality factor of the laser beam, we have a Q switched laser. So what do you mean by a Q switch? We'll be discussing in the next slide. Q switch laser also produces a pulsed laser output. Small pulses which range from micro to nanoseconds in duration are emitted from the laser device. Then we have the mode locked laser. Now here also pulses are obtained. It is also not a continuous wave laser, right? Pulses are obtained, and this is again a method. Both Q switching and mode locking are methods to enhance our power output of a laser beam, right? We will be discussing now Q switching and mode locking. So what is happening in Q switching? Uh, the in Q switching, what we do is we have this laser crystal or whatever the laser medium we have, and then we have placed a Q switch next to this laser crystal. What is happening is incident light is being radiation falls on this crystal, and then emitted light is traveling along this direction. Instead of directly reaching this reflecting mirror, it has to pass through this Q switch. What we do is we switch it off for a while. Now when we switch it off, what happens is they when we switch it off, what happens is the light that is being transmitted from this laser crystal towards this Q switch is stopped here and is again asked by the switch to return the light in the backward direction. So this mechanism by which the Q switch returns back the light to this earlier reflector, it is known as feedback, right? This Q switch gives a feedback again to this earlier mirror, right? Then after some time, after a cycle, this Q switch is then turned off. Now what happens is that the light which has traveled in this direction, now we have a large amount of radiations in this segment of our laser device. Now this Q switch is now off. Now all the light will travel this way. Now what happens is that when the light passes through Q switch to this reflector, there is an amplified radiation now. Why? Because we have gathered the radiation here for a small period of time after multiple reflections, and then suddenly we allow them to pass through this Q switch. This sudden passing of radiation, which is intensified in nature, allows us to get a pulse, a beam of laser light which has a better power out, which is better intensity. So, and what are the possible ways by which Q switching can be done? There are two possible ways. One is known as active Q switching, and another is called passive Q switching. Active Q switching is that we can turn it on off by external intervention, and passive is where we have just added that Q switch over there, and after that the procedure takes on its own course. You need not intervene, right? Active is generally for active Q switching, mechanical methods are generally used, and for passive, chemical absorbers are used. So you need to see your textbooks. What are the various methods by which Q switching is obtained? All right. Then what is mode locking? Mode locking is again a procedure by which we enhance the power output of our laser device. Now in the process of mode locking, what we do is, now when a laser light is just produced, or the light that is inside traveling and being reflected multiple times inside the laser medium, it has random phases. Okay. Now if we lock these phases in a uniform manner, then we have an ultra short pulse of high intensity. We can obtain that. Okay. So this is called mode locking. And what are the different methods? Again, there is active mode locking and there is passive mode locking. Active mode locking is generally done by inducing an electromagnetic field which modulates the modes of the laser light, right? And then there is passive mode locking, in which we include saturable absorbers inside the laser medium. Again, look into your textbooks how mode locking and Q switching are obtained. Then finally we have types of lasers. Now on the basis of what kind of active medium we are using, they can be classified into 5 types. Semiconductor lasers, where the active medium is a semiconductor. Then we have liquid lasers, where the active medium is a liquid, fiber laser, solid state laser, and gas laser. First of all, gas lasers. As it is clear from the name, the active medium will be a gas or a mixture of gases, right? They have wide applications. They are generally the pumping scheme in these are generally the atom-atom collisions, or the electrical excitation is done to excite the atoms and to pump the ground state atoms to the excited state. The most common type of gas laser is the carbon dioxide laser and the helium neon laser. Helium neon laser, it produces a red light laser, and it is very commonly used, generally used in lab experiments. Helium neon laser. Carbon dioxide laser has more industrial uses. It is also one of the most widely used lasers. They're easy to handle basically. Then we have solid state lasers, where the medium is a solid. Most common and very early form of laser it was a solid state laser, that was ruby laser. Ruby laser is basically where the active medium is ruby crystal. The ruby crystal is basically aluminium oxide, and aluminium oxide is some of the sites, vacant sites in the aluminium oxide crystal are filled with chromium atoms. Chromium, and this chromium impurity, addition of this chromium atoms, it gives its peculiar red color. The red color of the ruby crystal is because of these chromium ions. Now these chromium ions, they help us in creating metastable states inside aluminium oxide. So this crystal, ruby crystal, is an ideal example of a lacing medium, right? So solid state lasers, they are generally ruby not as prominently used as gas lasers. Their output is comparatively, gas lasers output is better than solid state lasers, and they are mostly used in LiDAR technology. LiDAR technology is kind of remote sensing technology like radars. So LiDAR is also a remote sensing technology. Most of the times it is used to survey the surface of Earth to look for different minerals inside the Earth's crust, right? Or they are also used in medical treatments also, like for hair removal or kidney stone treatments. Then we have fiber lasers. Fiber lasers are similar to solid state lasers. Instead, now what we have is, instead of a solid crystal, we have fibers, optical fibers, which are used as lasing medium. They are easier to handle. Their power output is better because you already have a uniform pathway for the laser to travel inside an optical fiber. The light is better intensified. Then we have semiconductor lasers. Semiconductor lasers, we exploit a PN junction to make a lasing device. Now the laser pointers and laser scanners, all these the devices, the lasers they use, they are generally semiconductor lasers. Then we have liquid lasers or dye lasers. What happens in liquid lasers is we have mixture of dyes, liquid dyes. Dyes means they're colorful, right? And they are used for constructing laser beams. Now they are also very widely used in industry, research and medicine. Now what special property these liquid lasers have is they are tunable. What do you mean by tunable? That you can control the wavelength or the color of light while the laser is in operation. Okay, if you want some other color light, you can simply switch over to some other color light, or the wavelength or frequency of the emitted laser beam can be adjusted according to your need. But that does not mean that all colors are possible. It depends upon the kind of dyes mixture you are using, what all colors it can give, right? So they're tunable lasers and they have very wide range of applications. And then these are the broad applications of lasing devices. Most of them I have discussed when I was discussing the types of lasers. They are used in medicine, in surgery. They are extremely used in, they find a lot of applications in the field of medicine and surgery. And then obviously for welding and cutting, they are high intensity laser beams. They can cut through materials. Okay, then they are for surveying and ranging, as I have told, that they are used in LiDAR systems for remote sensing. And then for communication, obviously, because they can travel to a large distance without losing much of its intensity. So they are used in communications. And then heat treatments for basic for various metal objects. Because they have a lot of power concentrated in a small amount of an area, it can be used to heat or anneal in the field of metallurgy. So this lecture covers almost, it touches almost all the topics of your syllabus. So I would like you to, after watching this video lecture, to go through your textbook, go through your syllabus. Once you go through this video lecture and after that you read your books, it will be more easier to understand the mathematical portions. Right? First you need to have a basic understanding of the subject, and which you will find this lecture very useful for that. For any other doubts and clarifications, students can ask in the class. Thank you.